presentation on the topic Instrumentation Amplifier. So what is Instrumentation Amplifier? Instrumentation Amplifier is a kind of differential amplifier with additional input buffer stages. The addition of input buffer stages make it easy to match the amplifier with the preceding stage. The common term for this condition is we know that is the impedance matching. Instrumentation are commonly used in industrial test and measurement applications. In the previous slide, we get the basic definition of the instrumentation amplifier. In this slide, we will talk about the features that the instrumentation amplifier shows. All the features are like it is having a high CMRR. CMRR is nothing but common mode rejection ratio. And low offset voltages, high input impedances, and high gain, etc. and all. And it also have an external or internal resistance. So all these parameters we will see in our further slides. Now in the next slide we will discuss about the block diagram of an instrumentation amplifier. In this slide we will going to talk about the block diagram of an instrumentation amplifier. The first block in an instrumentation amplifier is always be a transducer, because the quantities which are required to be measured and controlled are always in the physical form, and these physical quantities cannot be directly applied to this indicator or a display unit of an instrumentation amplifier system. Therefore, it is very much important to convert these physical quantities into an equivalent electrical signal, which is done by the help of this device known as transducer. It will convert the physical quantities into an equivalent electrical signal. The output given by the transducer is basically a low-level electrical signal, which is insufficient to drive this instrumentation amplifier. These two blocks, that is the preamplifier and the instrumentation amplifier, are basically the instrumentation amplifier system. So the low-level signal will get amplified to a high-level signal with the help of this preamplifier, to a high-level signal, which is sufficient to drive this instrumentation amplifier. Now the instrumentation amplifier is nothing but a signal conditioning unit. Instrumentation amplifier will just do the operations such like as amplification, attenuation, integration, differentiation, and many more. So the output of the instrumentation amplifier will be fed to this indicator or a display unit, where the indicator and display unit will convert the electrical signal into a visual signal, into a visual quantity that can be seen on the screen or can be pointed on the indicator. So this will be the output, which will be shown to the corresponding input, which is fed to this transducer and will be gathered by the amplifier. In the next slide, we will going to talk about the characteristics of an instrumentation amplifier. In this slide, we will going to study about the characteristics of instrumentational amplifier. So the first characteristic we study will be the precise amplification of low-level signal. The instrumentational amplifier is expected to amplify the low-level output from the transducer. Therefore, the gain of the instrumentational amplifier required to be finite, and it should be as high as possible. The gain of the instrumentational amplifier required to be 1000, and it should be accurate and stable, so that the instrumentational amplifier can provide a precise amplification. The second requirement that needs to be fulfilled by this instrumentational amplifier is the low noise. So we know that the instrumentational amplifier is nothing but a difference amplifier. So the difference amplifier having capability of rejecting the noise present at its input. So requirement of instrumentational amplifier is very much important when it is used in the biomedical applications, as these signals come from the patient's body, and therefore the output is required to be very much accurate and stable. Because of this, the noise present at the input of the instrumentational amplifier is required to be as low as possible. So the third characteristics we will study is the low thermal drift. As the parameters of the instrumentational amplifier is required to be constant with variations in temperature. So the parameters such that the parameters are not supposed to be changed with the change in the temperature. Next characteristic we talk is the high input impedance. As we know that the instrumentational amplifier are made up of op-amps, so ideally the input impedance of the op-amp is required to be very much high. Therefore, in case of instrumentational amplifier, the input impedance is required to be very much high so that they can avoid the loading effect or eliminate the loading effect. Next, we will talk about the accurate closed loop gain characteristic. So this characteristic and this easy adjustment of the gain characteristic are interlinked to each other. So the gain of the instrumentational amplifier is not only required to be accurate, but it should be adjustable easily. So the adjustment can be done by using a potentiometer. So when we vary the value of the potentiometer, the gain can be easily adjustable. Now the next characteristic is the low power dissipation. So in this the power consumption by an instrumentational amplifier should be as low as possible so that it will produce less heat that can improve battery life if it works on the battery. The next characteristics that should be fulfilled by the instrumentational amplifier is high CMRR. This is the main characteristic. CMRR is nothing but it is the common mode rejection ratio. So the common mode rejection ratio is basically used to reject the common mode signals present at the input of any amplifier circuit. So the most commonly signal present at both input of the op-amp is nothing but the noise signal. Therefore, it is required to be. So CMRR should be as high as possible practically, but it should be infinite periodically. So now the next parameter we talk is the high slew rate. This indicates that there will be less undistorted output in case of instrumentational amplifier. If this new rate becomes infinite, this slew rate becomes infinite or it becomes high. The highest slew rate also provides undistorted output voltage swing at the output terminal of instrumentational amplifier. Now in the further slides we will see about 3 op-amp instrumentational amplifier circuit, and we will also calculate the output voltage expression for it. In this slide we will going to study a typical 3 op-amp instrumentational amplifier circuit diagram. As seen from the figure, this is the op-amp 1 A1, this is the op-amp 2 A2. The op-amp 1 and op-amp 2 are known as the voltage followers, and these are also known as unity gain buffer because the gain of the voltage amplified is equals to 1, as the inverting terminal of the op-amps are directly connected to the output. Similarly for this case also, the inverting terminal is directly connected to the output. The op-amp 3A3 is the differential amplifier op-amp. So as seen from this circuitry, this is the partition line and the left portion of the circuitry is known as the voltage buffer circuit, and similarly the right hand portion of the circuit is termed as differential amplifier circuit. As can be seen from the figure, the R gain is the potentiometer is basically a potentiometer which is used to adjust the gain and also the accuracy of the amplifier. As seen from the figure, this is the voltages V1 and V2. So this voltage V1 and V2 are the supply voltages which are fed to the non-inverting terminals of the op-amp 1 and op-amp 2 also at the non-inverting terminals. Due to the concept of the virtual ground or virtual short, as they are voltage follower circuitry and unity where gain buffers are there, so therefore their terminals are short circuited and the voltage at the non-inverting terminal will occur at the inverting terminal. Same voltage will occur at this. So V1 will occur here and it will carry till this point also, and so from here the V2 will be occur at this inverting port of this op-amp 1. So V2 will also occur till here. Thus the value of R1 and this voltage also same, and this R3 is the input resistances. This is also same for this. And in this voltage differential amplifier circuit, this R4 is the feedback resistor. In the further slide, we will carry out the operation of the determining the output voltage equation. Now we will see the output voltage expression. V0 is nothing but equals to voltage follower gain AVF multiplied by the difference in the two input voltages of the op-amp. Vd is nothing but V01 minus V02 as here compared here. Now if we apply the current equation, that the current here will be same. If we write the voltage drops, the voltage drop across each unit will be equals to each other. So apply the Ohm's law between the point this A and this point B. So V01 minus V1 over R1 is equals to V1 minus V2 over R2 is equals to V2 minus V02 over R2. Now first we will compare these first two equations, that is V01 minus V2. V01 minus V1 over R1 is equals to V1 minus V2 over R2. From here we can get the results of V01 and can be termed as equation number 1. Now we will calculate the value of V02 from these two parts of the equations, that is V1 minus V2 over R2 is equals to V2 minus V02 over R1, where V02 is written as R1 over R2, V1 minus V2 minus V2, and it is under equation set 2. Here we will talk about the output equation of the differential amplifier. So here the output of the differential amplifier, that is A3, will be given as shown in this block. V0 is nothing but minus times R4 over R3 into the difference in the voltages, that is under the input voltages, Vd. So R4 is the feedback resistance and R3 are the input resistance. The negative sign is taken over here because the inverting terminal is connected to the output of the op-amp. Now the voltage equation is shown in this block. Now we will substitute the values of V01 and V02 over here in this equation, and as we have calculated the values of V01 and V02 in our previous slides. Now when we substitute the values of V01 and V02, we will simplify these equation now by taking V1 minus V2 as a common. So V1 minus, we take just common out, V1 minus V2, it will left with 2R1 over R2, V1 minus V2. Now if we take this V1 minus V2 out of the bracket, then we will left with this minus R4 over R3, 1 plus 2R1 by R2. So we have, by our previous studies, we know that the output upon the input is known as the gain of an amplifier, that is V0 upon the difference in the input voltages. V0 over V1 minus V2. Here this minus R4 over R3 times 1 plus 2 over R1 by R2 is nothing but the gain of an instrumentation amplifier. So this is the overall gain of the amplifier we have calculated. Thank you. That's all from my presentation. That's all for about typical 3 op amp instrumentation amplifier. Thank you very much.